something, the Fourier transform when ft a t square pi over a exponential minus 4 a omega square this one very important properties. And if ft is given by this, one zero, otherwise then two omega sine omega, right? So we can check that from the previous. Looks like I have stopped the recording, so I'm going to repeat it again. Oh, so when I switch the mode, maybe if I switch back to different program, then it might automatically turn off the microphone. I didn't know. So the complex conjugate of a plus ib is defined as a minus ib when a and b belongs to R, real number. And this complex conjugate is known in Korean as Fourier. So absolute value of Fourier transform is actually the multiplication of f omega with its complex conjugate, right? That's the absolute value. So square is a plus ib times a minus ib. So it's integration of minus to infinite. We have two integrals. One is ft, and the other one is ft prime complex conjugate I omega t exponential I omega t prime dt t prime. So I'm going to continue this integral. So just remember that. Oh, sorry. So repeat this again here. The first one is ft prime complex conjugate exponential minus I omega t exponential I omega t prime dt prime dt. So complex conjugate I omega t prime minus t dt prime dt, which is actually this one, right? So what happens if we integrate this Fourier transform from infinite to infinite d omega? Then let's conjugate t dash exponential I omega t prime minus t omega t prime t studied this integration before, right? What happens if I integrate from minus omega to infinity of exponential I omega t prime minus t over d omega? Nothing but delta function, right? So this is actually 2 pi delta t prime minus t. So it becomes 2 pi ft f star t prime delta t prime minus t tt prime tt. So what happens if we integrate over tt prime with f star t prime with delta tt prime? So it's nothing but 2 pi ft f complex conjugate t dt is 2 pi. So we have very important result. So the absolute square of a Fourier transform, if integrate from minus infinity to infinity of d omega, same as 2 pi times the absolute square of original function over dt. This is a very profound result of a Fourier transform. So it has a name, Parseval's theorem. So we can regard this way. Ft is a function in time domain. Its Fourier transform is a function in the frequency domain. And absolute square of a function is corresponding to the energy. So the energy in the time domain, sum of energy in the time domain is the same as the sum of energy in the frequency domain. So that's actually what happens when somebody talking over the phone it's it can be your iPhone or Galaxy or whatever. Something, oh, how should I say? It's not good. Let me do a better cartoon picture. Over something, over she's holding this. I'm calling somebody. So when I speak, it's a function of time, right? So basically, this is then it's propagating over the space, over the electromagnetic wave in terms of a frequency function. So that's how you can transfer the vocal energy when you talk to somebody, and it's a function of time, right? It's like my speaking, the way I talk now is a function of time. So something like this, and t, and then it's transformed to something like this in omega, and so the energy, total information or total energy in the time function, when integrated over certain frequency, like a minus infinity to infinity, is preserved in the frequency domain function, and then can be converted back to ft square again, right? So you can somebody can actually listen to your talk over the phone, but process is the following. My cell phone transform my speaking or my talking or my voice energy into the frequency function, and then transmit over the space, and the receiver transform the frequency function back into time function. That's how Fourier transform works in our real life. But also Parseval theorem can be applied to calculate a very difficult function. For example, so let's start with the Parseval theorem. When ft is given by this, we know that f omega is sine omega over omega, right? That's your ft. That's your f tilde omega. So if I ask you to calculate this integral, what do you do? Use Parseval theorem. The same as this, right? Same as 2 pi dt, right? But ft is simply the square minus 1 to 1. So that integral is actually 2 pi times minus 1 to 1 dt, right? So that's 4 pi. So it's pi. So some very difficult integrals can be calculated using Parseval theorem. Actually, if you take a look at the previous quiz, then I ask you slightly tweak the problem. So, for example, I can tweak the problem a little bit to calculate just switch omega by x. How do you do? If I ask to calculate this function, sorry, I just changed the variable from omega to x, right? But still you can see that you can apply Parseval theorem. So 0 to infinite is actually 1/2 to this, right? And you can transform in, just change your variable, omega square, sine square omega d omega. Then you can see that you can use Parseval theorem, right? So it's a 2 pi 1/2 times 2 pi times that function. So that is actually pi over 2. So Parseval theorem can be also used to calculate some complicated function. And maybe I will let you give it time to copy. So this result can be modified. This problem can be modified a little bit. Can I move on? Okay. What if ft becomes tft? What is the Fourier transform? So tft exponential minus I omega t dt. Simplest way is by differentiating by omega. Correct? So this t in front of ft can be actually obtained by integrating this function by omega. So if we integrate by omega exponential minus I omega t, we have a minus I t in front. So minus I can be cancelled by applying I. So this is the same as this, right? So for example, ft is given by this. So this is actually t times this, right? 1, 0. Otherwise, right? So what is f omega? So actually I d omega d. We know this Fourier transform, which is twice of sine omega over omega, right? So omega over 2 sine omega. So I, 2i times omega over cosine omega minus omega square sine omega so twice I omega square over omega cosine omega minus sine omega. So the absolute value square is four times omega fourth omega cosine omega minus sine omega square. So if you integrate this, what happens? Maybe we have a space here. So 4 times minus infinite omega 4 omega cosine omega minus sine omega square d omega. You can apply Parseval theorem, right? So it's 4 times 2 pi times minus 1 to 1 t square dt is 8 pi divided by 3 over 2. So 3 over 16 pi, right? 4 times, this is a 2 pi. No, there is no 4. There's no 4, right? 2 pi times 2. 2 times, that's the square. 4 has to be 2 y's. Pi. So you can use this space. This is 3, this is 4. So actually omega fourth omega cosine omega minus sine omega square d omega is actually pi over 3. Very interesting, right? So I can tweak it's time to copy, right? So can I move on? So actually, maybe I can ask you to, in the actual final exam, the potential problem can do like this. Calculate 0 to infinite, x to the fourth, x cosine x minus sine x squared dx. Using Parseval's theorem. So what do? You now know how to do that, right? Because you know the original function. So actually, and then apply the Parseval theorem. T squared dt. So this is actually pi over 6. What about if t to the n of t? The Fourier transform would be I d omega d n, right? Times f to the omega. So try, because I already give you t to the 0, t to the 1, right? So ft can be something like this. Ft is something like this. Then try t square ft, t cube ft, maybe t to the 4th ft. So that is I d omega d square f omega, right? And then one of the three can be asked in final exam for calculating the integral over Parseval theorem, using Parseval theorem. So it's a good candidate. So the final, something like this, right? Square, right? D omega. Same as 2 pi t to the square ft. Not this way. T square ft square dt, right? Or n. So n equal 0, 1, 2, 3, 4. Okay. To make your life easier, I will just make it 2, 3, 4. And just pick one of them. Or 5. So everybody understood my intention? This is going to be definitely the final exam problem. So you already know one. 2, 3, 4. Twice and 3 times will be right. 3. That can be a good problem, right? Of course, another possibility is Gaussian. Because the Fourier transform of Gaussian is Gaussian. So you take absolute square, still Gaussian. This part is still Gaussian. But no, it's not very easy. So forget about Gaussian, just this function. And maybe you can take a break. Okay, so many students ask me why TFT becomes transformed with I omega. So maybe I was a little bit too fast. What is this? If you differentiate exponential minus I omega t by d omega, what do you get? it exponential minus I omega t, right? So I d omega d exponential I omega t is t exponential minus I omega t, right? So if you differentiate this whole thing, dt, since integration is over dt, so d omega can be put into the integrand. Right? So it becomes exponential minus I omega t, tft, dt. So if ft is transformed into f tilde omega, then tft becomes I d omega d f tilde omega. And like the same way, t to the n's ft is transformed into I d omega d to the n f omega. Is that answers many of the questions that many of you asked me? So I hope that answers the question. And let's go further one more topic that okay, so convolution. Convolution of ft and gt is defined as the following. This is this is called convolution. So let's say if ht is defined as ft of gt, then we are interested in what is the Fourier transform of ht. Omega t dt, which is ft prime gt minus t prime exponential minus I omega t dt prime dt. And I guess we need more space. So can I go on? T prime, right? So f, let me see, ft prime gt minus t prime exponential minus I omega t dt dt prime. And we can actually insert 1. T prime dt prime. So this is basically 1, right? So I haven't changed anything. However, it can have something very pronounced effect. gt minus t prime exponential minus I omega t minus t prime t prime dt dt prime. So let's do the t integration first. So we can put this ft prime exponential minus I omega t prime, and then do this integral first. G t minus t prime exponential minus I omega t minus t prime, and dt dt prime. So here you can change t minus t prime as u, right? Then infinity minus t prime is infinite, minus infinity minus t prime is minus infinity. So this integral is actually minus infinity to infinity ft prime exponential minus omega t prime gu exponential minus I omega u du dt prime. But this is nothing but g omega, right? So maybe you can have another space here too. So then it becomes minus infinite ft prime exponential minus omega t prime dt prime times g omega. But this is a f omega, right? So the whole thing is f tilde omega times g tilde omega. So we need time, right? So convolution is really, really important. So, if HT is a convolution of 3T, then so let's study some particular example. So let me check. I don't exactly remember that. So let me check out. So example, Ft is T Gaussian and Gt is otherwise. So this is something like that, Gt T minus 1 to 1, 1, this is called the Gt. So it's more like a filter, right? Filter. You just accept the signal from certain range and reject everything outside. So let's calculate this convolution first. Convolution is, maybe you can put this way, Gt prime, Ft minus T prime, Tt prime. Then the integration is from minus 1 to T minus T prime exponential minus a T minus T prime square Tt prime, right? So let me see, set T minus T prime as U, then Tu is minus Tt prime. So this is the same as so this is when T prime is minus 1 is T plus 1 is T minus 1. This is U exponential minus a U square minus Tu, right? So this is 2. Then the whole integration is T minus 1 to T plus 1 U exponential minus a U square Du, right? So this is T minus 1 T plus 1 exponential minus a U square u du. So let's make a space here, 3. So say v as a u square, then dv is 2u du, right? So our integration is actually t minus 1 square, t plus 1 square. Exponential minus AV dV. So this is 1/2 minus A exponential AV t plus 1 square t minus 1 square. So where is our space? More space here. That's 4. Sorry. So we have, what do we have? 1/2a exponential minus a t minus 1 square minus exponential minus a t plus 1 square, right? That's your ht. So that is your ht, convolution integral. However, the Fourier transform is easy, right? Fourier transform is h omega. According to, we have this. So that is I t omega d root a over pi exponential minus 4i omega square times 2i over omega sine omega. So that means the Fourier transform of this function exponential minus I t minus 1 square minus a t plus 1 square is the same as I this. Omega 분의 2 sine omega. This is so Fourier transform. So that is how you obtain the convolution integral. Maybe I can ask. Maybe I can use this as a convolution integral as a original problem, and then you can find the Fourier transform. But so that's about it. So I may ask one problem in convolution integral, but most likely Parseval theorem. So that's about the class this semester. And I briefly discussed what we studied so far, right? So can I move on next? So let's discuss final exam. last thing. So in this semester, we studied a matrix, right? It's a matrix multiplication, determinant, inverse matrix, and eigenvalue problems, and spectral theorem, polar decomposition. We learned a lot, right? And for the differential equation, we learned logarithmic derivative, and that's actually first order ODE. And we studied homogeneous ODE, two cases, constant coefficient equidimensional case, and of course inhomogeneous differential equations, ODE, normally second order, and Laplace transformation, and Fourier transformation. And so exam will be 11 to 2, 3 hours. So you can prepare 3-page cheating sheet. It's allowed 3-page. So one good problem is polar decomposition. Right. So polar decomposition, actually you need to calculate determinant, eigenvalue problem, and you have to know spectral theorem. The polar decomposition actually requires these three. Determinant, eigenvalue, all three. So I think polar decomposition can be a very good candidate of a final. And we have seen that it takes about half an hour or very easily. If I ask it 3 by 3, that will be very long time consuming. So one problem left over is inverse matrix, so that's also a possible candidate, right? So for the linear algebra part, inverse matrix and the polar decomposition is a good candidate. Because polar decomposition is a very good problem. You need to have eigenvalue problem knowledge, spectral theorem and determinant. So it asks for 3 knowledge, and the inverse problem is you need to have a determinant, right? So this is a good candidate. And of course, there is one. I can ask you one. Laplace transformation may be one problem. And Fourier transform one. Most likely Parseval. And 2 problems. One inverse matrix, finding an inverse matrix, one polar decomposition. How many? 1, 2, 3, 4, 6. Oh, no, there's one more, right? 7. So 2 problems in linear algebra, and definitely 1 problem in the logarithmic derivative and Parseval, and 1 problem for the homogeneous space, maybe with a multiple root. And 1 problem from inhomogeneous ODE, 1 Laplace transformation, 1 Fourier transform. So you have a 7 problem in 3 hours, and that will make you very busy. So how many of you have an exam at 2? After my class, there are some students that have exam at 2. How many? There was one student. 2시에 시험 있는 사람. 1, 2, how many? 2, 3, 4. 2시? 2시에 시험 있는 사람. So for those students have a 2 o'clock exam, should contact with my student, TA, then we have another final scheduled at 11, the day before. Different set of problems, but similar difficulty level. And so they will be given equal score. So if you have an exam at 2 o'clock, should contact Mr. Sang-won Park after this class and arrange for the final exam at the day before 11. 한국말 한번 다시 얘기해요. 2시에 시험 있는 사람은 그날 파이널 데이에 2시에 시험 있는 사람은 만약에 본인이 원하면 11일 날 시험 볼 수 있어요. 다른 문제로. 그러니까 난이도는 비슷하고 아마 그 시험 레벨은 비슷한데 다른 셋 오브 프로블럼으로 볼 건데 우리 조교 학생한테 컨택을 해서 스케줄을 잡도록 하죠. 이번 시험 끝나고 그리고 오늘 수업 안 온 학생한테도 연락을 해서 만약에 그 전날 시험 볼 사람은 그렇게 해주세요. Okay, that's the end of this semester. So, thank you. Thank you for your patience. 그렇죠. 예. 물어보세요.
저번 시간에 연습하실 때
근데 뭐가 문제지?
그냥 그때 출석했다고 했는데
아, 그날 5점짜리 시험 본 거? 오케이. 즐겨주세요. 그러니까 만약 전날 시험 볼 사람은 미리 약속을 잡아서 11일 날 볼 거예요. 이번 학기랑 지난 학기랑 난이도가 어때요? 이번 학기 누구 어려웠어요? 네. 네.
저희가 이걸 가지고 저번 구주차 수업에서 이걸 가지고
중분했을 때
계속 이렇게 이것도 솔루션 뭐 이렇게 솔루션해서 결국 여기까지 솔루션이다. K-1까지만 솔루션이라 했는데 저는 이게 왜 K-1까지인지 좀 의문이 드는 게 계속 그냥 얘 옆에 그냥
이렇게 될 거 아니에요. 만약에
네.
원래 거는 이걸 집어넣으면 뭔지 모르지만은
네.
뭐 람다 마이너스 람다 제로의 K신
네.
람다 마이너스 람다 1 뭐 이렇게 곱해졌을 거 아니에요.
네.
n 그죠?
네.
exponential
네.
람다 x에서
네.
여기다가 이제 람다는 람다 제로를 대입한 게 0인
네.
거잖아요. 그죠?
네네.
한 번 미분하면 어떻게 돼요?
한 번 미분하면 K 빠지고
이쪽은 K의 람다 마이너스 람다 제로의 K 마이너스 1. 그 다음에 이거는 그대로 있고 이쪽에 미분하는 거 남겠지?
네.
그죠? 쭉 K번 미분하면
그래서 이게
K 마이너스 1까지만 미분해야
네네.
이게 살아남는 거거든.
네. 이게 막 살아남는데 이 부분에서 약간 이해가 안 가는 게 이게 0인 거를 알 때
이게 0 이거지. 람다가 람다 제로일 때.
네. 이거일 때
그럼 제곱만 해봐. 제곱만 해보면 쉽게 그냥.
네.
만약에 람다 마이너스 람다 제로의 제곱에 하나 더 있었다고 하자. 뭐 어쨌든 F 람다일 거 아니에요, 그죠?
네.
exponential 람다 x 그죠?
네.
두 번 미분하면 어떻게 되지?
두 번 미분하면
한 번 미분하면
이
람다 마이너스 람다 제로에 F 람다에 이거지.
네.
플러스 이건 그대로 남고
네. 이게 어떻게 되고
어쨌든 이쪽에 이렇게 되겠지, 그죠?
네.
맞나? 이거 미분하고 이거 미분하고죠.
네.
한 번 더 미분하면
한 번 더 미분하면 얘가 람다 마이너스
없어지잖아.
제로 형태가
F 람다에 플러스
네.
이거 미분한 건 조금 두 개 남겠지.
네.
그죠?
네.
근데 아무튼 이쪽은 0이 되는데
네.
이거는 0이 아닐 수가 있잖아.
네.
이게 살아남으니까.
네.
그래서 하나 전까지만 미분해야 돼.
근데 여기서 하나 궁금한 게 저희가 람다 제로일 때 이게 0이라는 걸 알고 있을 때
네.
그럼 이것도 0이고
그러니까 이걸 대입했을 때 이제 람다가 람다 제로가 대입해서 0이 돼야 되잖아.
네. 여기도 그냥
근데 이거는
붙은
0이 아니거든. 제곱하면은 이 텀 때문에 F0 람다가 있어서 뒤에 건 0인데 여기 살아남거든. 그러니까 이거는 0이 아니고.
제가 궁금한 건 람다가 람다 제로이면 얘가 0이고 그러면 얘도 0인데 0을 두 번 미분한 게
아직 0은 전이지. 아직 람다 제로를 제입하기 전에 미분하는 거지. 그냥 람다의 함수일 때로 하고 나서 대입을 하는 거지.
순서가 잘못됐구나.
그렇죠.
아 그렇구나.
그러니까
네.
두 번 미분한 거는 0이 아닐 수가 있어. 왜냐면 f 람다가 0이 아닐 수가 있지. 람다 제로가 0이 아닐 수 있잖아.
아 잘못 생각했구나.
음.
그래서 저는 그냥 왜 자꾸 0에다가
네.
미분을 몇 번을 하든 상관이 없지 않나?
근데
이게-
0이 아닌 거죠.
아,
람다로 미분을 다 하고 나서
미분을
나중에
하고 나서.
대입을 해야 되니까.
아,
Yeah. Like what? Oh, maybe you need